Welcome to Spring LIB.
Great. Now we've got the following structure. Redraw this here. We've got to determine which parts of these various functional groups will be capable of hydrogen bond donor, donating hydrogen bonds, or accepting hydrogen bonds, or what are hydrogen bond donors and what are the hydrogen bond acceptors. And we'll also have to total up the number of each. So let's recall what hydrogen bond donors look like. Hydrogen bond donors, which I'll draw, a D to represent donor, should have a bond to a proton. And that bond should be polarized in such a way that that hydrogen, partial negative, partial positive, is attractive to partially positive hydrogen bond acceptors. So we need a polarized bond to a proton. So carbon hydrogen bonds aren't polarized enough to be, considered bond donors. But typically any heteroatom, as they're called, so heteroatom meaning non-carbon, non-hydrogen, hydrogen bond is. So OH and NH are the classic hydrogen bond donors. And in fact, as we look around this molecule, we see we have an amine and we have a carboxylic acid over here. And each of them have a heteroatom to a hydrogen bond. So it looks like in terms of acceptors, that's what we've got. We've got two hydrogen bond, in terms of donors, that's what we've got, two hydrogen bond donors. Now we need to consider what our acceptors are. Okay, so again, what we're looking for is partially negative or polarized bonds. And more specifically, we're looking for a high level of charge density in these acceptors. That is, consider molecules such as I minus, and that it is much larger than, or maybe not I minus, but consider if we had like a carbon over here in a bond to this iodine, and versus having a carbon bound to, say, an oxygen, maybe an OH, and how much smaller this oxygen is. The negative charge or the partial negative charge on this polarized iodine is much more diffuse. It takes up much more space. It's not, it's like comparing like a beach ball to like a baseball. The negative charge is all spread out, and for that reason, it's not as attractive to protons, which are also small charged species. So small charged things attract other small charged things, and big charged things attract other big charged things. So the other component of being a hydrogen bond acceptor is not simply being, you know, partially charged or polarized to be more negative than the carbon it's attached to, but it should also be roughly smaller. So in fact, for that reason, we don't consider chlorines or in fact any hydrogens to be hydrogen bond acceptors. So we can actually ignore these chlorine molecules. Chlorine's about the cutoff for that. So if you find in your class that you do treat chlorine as a hydrogen bond acceptor, that's because compared to all the other halogens like bromine or iodine, chlorine is the maybe the smallest without being fluorine. That kind of the cutoff is usually put here or here, depending. So check with your teacher. But in this case, we will not consider chlorine to be a hydrogen bond acceptor, despite the fact that compared to the carbon that's attached to, it is partially negative, but it's just too large to be a effective hydrogen bond acceptor. Okay, so given that we're ignoring the chlorines for now, let's tally up our hydrogen bond acceptors. Well, nitrogens are also somewhat electronegative compared to the carbons they're attached to, and nitrogens make both hydrogen bond donors and acceptors. So this nitrogen is one. Any of our oxygens can serve as hydrogen bond acceptors. Right, so this oxygen right here, you can consider versus the carbon here, it's partially negative. Here's another oxygen, a couple lone pairs there. Here's another oxygen that's just like the one from before, partially negative. Same with this oxygen, would be partially negative compared to its proton or compared to this carbon on the left. So in terms of acceptors, we've got nitrogen, oxygen, 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 oxygen. That looks like we have 5 acceptors. 2 donors, that's the amine and the carboxylic acid, OH, and 5 acceptors. That's all of our nitrogens and oxygens.